And I'm going to get the student who's online to be with us now. So let me call and then do a screen share. All right. So on Monday, I forgot one thing. Monday was the due date of the CNF assignment. I completely forgot about that. Um, so what I'll do is to see if anyone wants me to go over the solution. If so, I can go ahead and do that. If not, we can move on. So go over? Okay. All right. So we can do that. Um, all right. So the assignment is about converting this expression into CNF. Now, you guys also remember that this is the first semester that I introduced the truth table method. So you can, if you want to, use the truth table method to come up with the CNF. How many people did that using the truth table method? Okay, two, three ish. Okay, that's good. Um, so the rest of the class, do you want me to go over the Boolean algebra method, or do you want me to go over the truth table method? Both? All of the above. All right, so we can do that. Um, all right, so I'm just trying to figure out what is the best way to do it. Okay, I think a text editor would be fine. So copy and then go to a text editor, just paste here. All right. All right. So what we'll do is to convert this into a CNF. And typically the way I do it is to get rid of the implication by negating the left-hand side of an implication and then or the right-hand side. So that's usually the first step. And I'm just going to write down here also, this is the definition of implication. And then we see that there's another implication in here, and I'm going to do the same thing. So we will end up with a bunch of parentheses because there's a lot of nesting. So in this particular one, we want to turn this into a or, and then we have to negate the left-hand side of the original implication. So now we have two applications of definition of implication. All right, so at this point, I'm going to apply De Morgan's law because we want to move all the negations to the inside as much as possible. So this one I will let it stay the same as it is right now. And then here we have the negation of the disjunction between not P and R. So we'll go ahead and do this as a double negation of P and the negation of R. And then the other side stays exactly the same as before. So I'm only doing one thing at a time. So this is the application of the Morgan's law. All right. And then what we'll do is we can do a little bit of simplification. I don't want to combine several steps into one because that's also, when I can easily make a mistake and not know until much later. So that's canceling out the double negation. And then two, I don't need the parentheses because I can use the priority of operators to know which one goes first. All right. So now we look at this and we have one more De Morgan's law to apply because this is a negation of this or. So we apply De Morgan's law one more time. And to summarize what we did before, I'll just call this simplification, which is getting rid of the double negation. All right, so now we have the negation of P and not R and the negation of Q and not S, and then the whole thing ORed with R and not T. And that's De Morgan's law again. And now we apply to De Morgan's law because we have a negation of an and here. We have another negation of another and over here. So now we end up with not P or not R and not Q or not S. and then we have the original or R and not T over here. So once again, this is the application of the Morgan's law. And then we do some simplification. Once again, I don't want to combine too many steps into one. So I'm going to do the simplification here as well as here. All right, so at this point, I can apply distribution. So we can apply distribution by saying not P or R, and not Q or S. Oh, okay, never mind. Okay, let me think about this. Yep. Oh.
Oh, at this point, I just distributed all of R and not T
Mm-hmm.
across. Okay.
All right. So which part do you distribute to what? Oh, okay. I see what you mean.
Yeah, so it would be R and not T or not P or R, and then R and not T or not Q or S.
Okay. So I think you're right, but I do want to kind of go through my own mind and identify the thinking process. Okay, in other words, how do I choose which distribution to use? So the first thing we need to remember is what distribution we are talking about. So we have A or B and C being distributed as A or B and A or C. That's one way of distribution. The other one is A and B or C being distributed to A and B or A and C. Oops, A and C, like that. So the question is, which one am I going to apply? Because I know one of them is going to be useful and the other one not so much. So we are looking at this OR being the last operator, and it matches this OR being the last operator. And so as a result, we can now distribute this into ORed with these things here. Um, I'm not sure whether that's going to be useful or not. So that's the thing. The other thing we can also do is to distribute these things. Um, so become one gigantic, OR with this thing, and then we end up with an even bigger, gigantic OR, and then we distribute everything, using the other method or using this particular method here, and so we basically cross all the terms. So let's go ahead and try that way. Okay, so we'll basically look at this term here, and because the other way doesn't seem to make sense to me.
I did it the other way after
You
the right answer.
so you did you use 11 or 13?
Uh,
It has to be 13, right?
I believe I used
11? Oh, right. It has to be 11 because the OR is on the outside. Yeah, unless you're doing this one, then you can use 13. Okay. All right, so let's do it that way. We'll try 11 first and see what happens. So now we have not P or R, and then we are ORing this with just R all by itself. And then we have an AND with, wait, okay, I missed one thing because it's the entire A, so this has to be that. And then we have the other one, which is not Q or S. And then this whole thing has to be ORed with R and not T. Okay. So at this point, we can now distribute, because with each one, we are looking at the same scenario as this one here. The pattern matches. So this one becomes So there's an OR, and then the other one has multiplication. So we're gonna use this pattern to match this particular pattern here. And in that, we have this entire thing matching A, this matching B, and this is matching C. Okay, are we doing okay so far in terms of understanding how I know which one applies? Is that okay? All right. All right, so let's go ahead and do that. Um, so that becomes not P or R as one thing, and then um, ended with not P or R or not T. Does that make sense? Are we good so far? Okay. And then the other side is going to be about the same thing. The entire not Q or S is our A, and then we have or R on one side, and not Q or S, and then now this time we have or not T on the other side. So now we do have a CNF, but we can simplify this CNF. So the way we can see that this is a CNF is we can dissolve the parentheses. There are many ways to get to the same spot. In previous classes, I just multiplied the whole thing out, and then it was kind of a bigger mess. So in this case, I can remove some of the extra parentheses. So this one is not needed anymore. This one is not needed. This one is not needed. And this one is not needed either. And now we have not P or R. And I can simplify that one out entirely. Okay, let me space out so you see which one I'm simplifying out entirely. And then I'll explain why I can do that. Okay, so give me a second to finish this part. All right, so you can see this whole thing here, which is not P or R or not T, is completely gone. So the question is, how can you do something like that? Because you in a conjunction of two terms where one is implying the other one, you can keep one of them and you can toss the other one. So in this case, this one here is more specific than this term over here. In other words, not P or R, if not P or R is true, then not P or not T also has to be true. Does that make sense? Let me just kind of make that point first. Question? Oh, okay. I thought you had a question. But does that make sense? So if that is the case, that means this is redundant. This is useless in a conjunction, because if this term is true, then this term is going to true also. So it becomes redundant in a conjunction. And that's why it can be simplified out. Are we okay? Yep.
What about the not T? Isn't that independent?
The not T. Okay, so let's check this out. Okay, so instead of applying the reasoning to a problem that we're trying to solve, we'll try to condense it to the simplest form that we can use, right? So what we're trying to ask is, we have A as an independent variable, and A or B, and B is independent to A entirely. And we are asking, is that really the same thing as A? That's basically what the question really is. Does that make sense? Okay. So how do we prove that? I mean, this is a technique that we have been using in this class for a whole lot of times already. Almost every single class, we go through this technique at least once. And what is that? Truth table. Very good. Okay, so we're going to use a truth table and find out, whether A and A or B is really the same thing as A when A can be false, B can be false, this is going to be false, and this is false. Okay? And when A is false but B is true, then this is still false, and so is that. Is that okay? Because this is one of the most important part is you can see that because A by itself is part of the conjunction, so that means if A itself is false, I don't really care about what B is. The conjunction between A and A or B also has to be false. And then the third line is A is true, but B is false. So in this case, A is true, so that means one side of the conjunction is true, but so is A or B, because if A is true already, I don't really care what B is, because A or B is guaranteed also to be true. So now we have A true and true, which is also true, and then A all by itself is just the first column, but I just make it a separate column here because it's one of the expressions that we want to establish equivalency. And then the last one is both A and B are true. So if they're both true, yeah, this one's true, and so is this one. So now we can see how the third column and the fourth column, which is also the same as the first column, they're identical, which basically means, whenever you have a conjunction between an expression and then the other side of the conjunction is the same expression or something else, I don't really care what the something else is. It is redundant. It's totally useless in the entire conjunction. Is that okay? So this is a simplification technique that looks really weird because of the way I use multiplication as a symbol and the way I use addition as a symbol. But remember, what looks like multiplication is conjunction, and what looks like addition is disjunction. Is that answering the question from earlier? Okay. All right. So that explains why this part is gone. Because the way to look at this is to look at this entire thing as what we see as A down in the truth table over here, and then just look at not T as B in the truth table down here. Is that making any sense? All right. And I believe this is the answer. There's no way to simplify any further because between these two conjunctions, there's no way to simplify this without turning this CNF into a non-CNF. All right. Any questions? Yep.
So when I was doing it, I forgot how I got there, but when I was applying negations in the first part, I flipped not R and T. So I put mine was essentially because I had flipped that back part.
On which line?
I think it was while I was doing like it was after I did the implications. When I was applying negation towards them, I also did negations on R not T, and then that gave me not.
Oh, okay. So this part you also negated this part.
I ended up negating that part too. So once I got down,
Then it will be different.
yeah, it was different. So then I had not P plus R and not R because I was like R not R kind of like make it a truth no matter what, because if it is R and not R, then it's true.
Right,
so
right.
then I got rid of that part. So then mine ended up being a little different because I flipped that not R into
Ooh,
yeah.
okay.
So I'm looking at this like,
All right. So you probably I will still get you, like partial credit depending on the correctness, the following steps. So as long as your steps are self-consistent, and I can see how one earlier mistake is continuing on, and still be consistent, I can still give you partial credit
yeah,
for
because I
that.
went through like pretty much everything else. It's just that I flipped that not R and T. So
I see.
like, I got close to that answer, but it's different because the R's and T's being switched around.
Okay. All right.
And there could be multiple possible solutions, right? Because I ended up with something very different for mine.
Is it longer or is it shorter?
It's shorter, and I ended up with just a conjunction of the independent variables.
Okay.
Yeah, mine ended up looking quite different, but it's still CNF because it's just each independent variable or the negation in one big conjunction is what I ended up with.
All right. Well, there's also an entire possibility that I just messed up in my own derivation. Okay, so now the question is, how do we check that? Okay, because how would I know that whether I made a mistake or not? Yep.
Make a really big truth table.
Yes, exactly. So once again, the answer is a truth table. Okay, so I think we're getting the whole idea of, maybe I should think about using a truth table, but no matter what the question is, like maybe I should think about using a truth table when it's just logic and Boolean stuff, right? All right, well let's do that. Okay, let's go ahead and use either a truth table, or you can write a program. It's up to you. Okay, Because you can also use a program because depending on how many variables we have, which is 5 in this case, so the truth table is going to have 32 cases. Um, the problem with using a truth table in a spreadsheet is expressing a Boolean expression in a spreadsheet is messy because a spreadsheet can only deal with prefix notation, which means you will end up with an insane number of parentheses, which is not good to have. So the other way to do this is to write a C program, have a like a 5 level loop, 5 nest, 5 deep, 5 level deep loop structure, and then just say for each variable, you just go okay, this one goes from 0 to 1, and while this one is a 0, or while this one is a 1, this one also goes from 0 to 1, and so on. So that's one way to do it. Do you guys want me to kind of illustrate that concept and kind of use that method to verify the answer? Yes. Say yes. Just say yes. Okay. All right. So with that in mind, okay, so let me go ahead and just do that. I'm just finding an excuse to write some code. That's all. All right, so this is, I can magnify this just one level. So this way I can still look at the equation. And on the other side, I can look at my actual code. Um, okay, I'll just call this check. This is just regular C, nothing fancy. I'll even do it without any subroutine, which is not recommended, if you're in any class. So we'll say, well, I can use int or unsigned, doesn't really matter. I think bool is still not existing in regular C, so I cannot say bool. Bool. Oh, it is. Okay, well, we'll give it a try. So we have p, it starts with 0. P is less than 2 because p can only go from 0 to 1. And that's one loop. Okay, and then we have this. Now we have Q, oops, Q, Q, and Q. And now we have PQR. And now I'm getting a little bit lazy and just substitute um, Q with R. Okay, there we go. And then do it one more time, 2 more times actually. This time we say substitute R with, oh, okay, it took out a 4, so I need um, R with a space in front or something that is not alpha in front of it. Okay, so to do this, okay, I have to remember my BI syntax, or I can just go ahead and do it by hand. Okay, fine, we'll do it by hand. So P, Q, R, S, and then finally we have T. Now, by the way, this is really not the best way to do this. The best way to do this is to use a recursive function, and also pass a function pointed to a function into the recursive subroutine. But this way is the most obvious. Okay, so now we are getting down to here. We'll say original, so bool original, and then we'll express the original using this particular notation. We don't have implication, so I'm going to define a macro here and say implies xy, so it becomes not x or y. And it's good to put parentheses around everything, so this way they can nest and I don't end up with a problem, then without the parentheses. All right, so the original is what? We have a implication of not P or R as one expression, and then we have Q and not as the other side, the right hand side of the implication. And this entire thing is inside another implication where when the inner implication is the left hand side, and then we have R and not T on the other side. And that's the original expression. And then we have the new expression, which is the CNF down here. So this is the CNF. This is blah, blah, and blah, blah, and blah, blah. This is the way I write it because I like to write it in terms of the structure. Um, and then we have not P or R. And then we have not Q or S or R. And then finally, we have not Q or S or not T. There we go. And we just have to find out whether they are the same or not, right? So now we can say, oh, forgot one semicolon. All right, so now we can say print, oh, okay, if original does not equal to CNF, and we say printf tech messed up. There we go. Wouldn't be the first time. And to get the indentation right, I just do an equal, close bracket, close brace, and everything now looks kind of nice. Set tab stop to 2. That was all good. Are we okay with this? More or less? And of course, it's not going to compile, or the compiler is going to complain because I need to include standard input output in order to use printf. All right. So we'll give it a spin. Okay, we'll see what happens. So save it. gcc-g-o check.c. And we have a bunch of problems because in C there's no bool. The bool type does not exist. Or standard bool. Yeah, but that means it's not in the language. Fine, standard boolean.h. I wonder what else is there. All right. Okay, we got one more problem, which is coming from my JavaScript programming bad habit, because in JavaScript you don't need a semicolon at the end of a statement. So on line 20, I just need a semicolon all the way to the end here. The tab stop went back to 8, which is the default. I did not have a configuration file yet to make it 2. So there we go. GCC, it's all good. GDB, check, there we go. And I am going to assume that I messed up somewhere. So I do want to know when I messed up. So I'm going to put a breakpoint on line 20, which means by the time we're about to print tech messed up, it's going to stop, and I will be able to read what is ABCD, PQRST. Okay, so I know in which case I messed up, and that will give me a clue as to which part of the derivation is incorrect. All right, so moment of truth, and it's an infinite loop. Okay, Control C, get out. And we want to find out where the infinite loop is because I think I forgot to change one of the, I forgot to increment one of the variables. So let's go ahead and print what is P, Q, R, S, T. Well, that gives me a general idea of where I messed up. I think it's between S and T, one of those two, or one of the loops responsible for those two is probably messed up. Oh, wait. Don't quit yet. Okay, because what I want to do is to single step at this point and find out where it is stuck. So it is the T loop that it is stuck at, and I wonder why that is the case. So T is just true. But I cannot, oh, let me see if I can cast it to an int. That's just 1. Okay.
If T is less than 2, the Boolean can never get to 2, right? Why is everything?
That's right. Okay.
Yeah, so everything is false. It's like all the loops are infinite.
That is correct. Because with a bool, which is a 1-bit integer, 2 is already exceeding that range. So I can't really use a conventional loop like this, because by the time T is true, if I increment again, it is still going to be a 1. Okay, so there's no easy way to do this unless I change all the type of bool to something else. I'll do a dirty solution. Pretend that you did not see this. I cannot remember. I think this is the way to do it. So what I'm doing is I'm doing a type definition to convince the compiler every time it sees the bool type, it is the same as an int. All right, so same deal. Put a breakpoint on line 20, run the program, and it ran without complaining, so tech did not mess up in this case. So thank you. But that was great debugging. Thank you. And I'm going to blame it on me not using the bool type ever in the C program. Yep.
So I think I figured out where my solution differs, and the exact steps might have been a little bit different, but at step 6 or after step 6, I used a Morgan's law to dissolve that last disjunction into a conjunction, and then everything's just a conjunction of variables.
Oh, so did you see this as one negation applied to the implicit conjunction here?
No, I think what I did was I think I applied a negation or something like that to make it work, and then I dissolved that last conjunction and ended up with just a string.
You dissolved this one.
Yeah, I dissolved the last. No, I dissolved the last disjunction. I mean.
The last disjunction.
Yeah.
You mean this one?
Yes. So I used
Oh,
the Morgan law to get
okay.
rid of that, and so then it just ends up being a conjunction of all of the
I
variables and
see.
negations.
Okay. All right. So when I see, when I grade it, I will see, where, the mistakes may be. Okay. All right. Okay. So, but did you guys, understand what the program did? Not the most elegant program at all, not by a long shot, but it gets the job done. Okay. It basically allows me to enumerate all 32 cases and figure out, which one is not matching, but they were all matching, so I did not make a mistake. Um, Not in this case, okay? Because I do make mistakes all day long. It's just not this one. Are there any questions? No other questions? Um, were there any difficulties when you guys were working on this? Any challenges and whatnot? Okay, I see a few people nodding. Go ahead.
Well, I guess just like up until step 8
Mm-hmm.
was pretty easy, and that was basically the roadblock for me. I felt like from there, that's when I really started to
Okay.
run around in circles.
Yeah. So at step, I had to think about it a little bit. And in previous classes, I would take it in the opposite direction. So I would actually do the distribution on this side, so end up with a bunch of, disjunctions. And then I would do one massive FOIL of the entire thing. So you end up with like gigantic and a lot of the expressions. And then I would clean up those expressions and simplify. Still be able to get to the end result here, but not nearly as quickly as, this method here. So there are different ways to get to the same result. It's just that some are what I would call scenic routes. So you just kind of go like, but you still get back to the right place. So, your final form may not be looking exactly like this, but as long as logically it is equivalent to this, it will still be okay. All right. Any other comments? Any other? Nope. Okay. All right. So I'm just looking at, okay, nothing from here. I'm just going to turn off my notifications, so we'll turn on Do Not Disturb. All right. So I think this, okay, if you guys have any questions about this, about the CNF assignment, just kind of bring it up. Assuming there are no further questions, I'm going to give you the next homework assignment related to CNF, because converting to CNF is really just one step to prove a theorem. So when you go to the next one, which is resolution and proof by contradiction, I just released that. Okay, so if you don't see it earlier, that's okay because I just released it like close to 3 o'clock. So this one starts with the answer of the previous one. So even if you got the previous one wrong, it's no big deal. I'm giving you a starting point. So the starting point is not P or R and not Q or R or S and not Q or S or not T. That's given to you. Okay, so you can use that. And what we want to do is to see if these two are theorems or not. So this is one gigantic mass all by itself, and then this is not so much of a big mass. Okay, so I want to see if this is implied by this. I also want to see if this is implied by that. But I don't want you to use just Boolean algebra to prove that. I want you to apply um, resolution to prove the two, to prove one way or another. So in order to do that, okay, I'm going to describe the steps really quickly, is for each proposed theorem, like this one, you have to negate it first. First step is to negate it, then convert the negated proposed theorem into its own CNF. Then append the CNF to this original CNF, and then perform resolution until you cannot perform any further resolution, or until you get to 0. If you can get to 0, that means the proposed theorem is indeed a theorem. If you basically do every single thing possible and you still cannot get to the 0, that means it is not a theorem. Is that okay? So that's what you guys need to do with, you have a week to work on this one. Yep.
So this is basically if P then Q, and then you negate Q, and then so you've not P as well.
If P is referring to this and Q is referring to that, then yes. But I want you to use the specific mechanism that we talked about in class called resolution. Is that okay? Because the whole thing is we want to mechanize. We want to make everything mechanical. And we already have a way to mechanically convert any expression into CNF. I just did that earlier using Boolean algebra, but I did not have to, right? Because I can just make the truth table and then apply the technique that I talked about the other day and end up with a CNF mechanically. So that means to convert this into a CNF can be mechanical. To convert that into a CNF can be mechanical. Once you have a long CNF, resolution itself is also mechanical. So the whole thing becomes mechanical, which means we don't have to do it anymore. We can program a computer to do it, which is kind of the objective of computer science, right? So for this one, once again, if you want to use the truth table method because this looks kind of messy and you don't want to do Boolean algebra, go ahead and use the truth table method to convert it into CNF. Same thing applies to this one. You can try one way and just kind of get to the point where you go like, okay, use the mechanical method. Fine, use the mechanical method. Not a big deal. Is that okay? All right. So if you do decide to use the mechanical method, you can leverage the code that I have already written. I am not going to give you the code because it is really just 5 embedded loops, right? So you can use the same structure here. The only thing is at the deepest part of the loop, which is where this part is. This is where you look at you print out. This is where you say I'm creating this disjunctive term because the expression turns out to be false. Then you make a disjunction out of the negated version of the CNF that would have otherwise made the expression true. Not sure whether I'm making sense or not. Am I making any sense? Maybe? No? Do you guys still remember the mechanical method to turn a expression into a CNF? Okay. Well, I did talk about it. Okay, so if you forget, you can go back to the earlier video and learn about that one. But all I'm trying to say is the structure is already here. You just need a conditional statement down here at the deepest level of the nested loops. See if that the expression that you're interested in is false or not. If it is false, then you need to do something about it. If it is true, you don't have anything to do. And then the output, okay, is going to be when you concatenate all the lines, all the outputs of this program, and concatenate everything with a conjunction, that would be the answer. That would be the CNF answer. So the overall structure is already done. You just have to change, this part here to whatever expression that is in the assignment. So this has to be turned into um, the C notation for Boolean expression, and this also has to turn into something that you can read in as a Boolean expression. So that part I cannot help, okay, because that part still requires a little bit of work on your side to convert these things into, well, not this one, sorry, I take it back. It's between this one and this one here. So these have to be expressed in as a C expression in the program. Unless you want to spend the time to make your own parser. And then you can generate that expression automatically. All right. Are there any questions? I don't think equal to and greater than is an operator in C or C++, because if it was, you can overload. You can overload the operator, and then you can actually have an implication operator. But I'm not sure whether, even in that case, whether the operator priority is going to work out or not. So I would just kind of do the manual translation from the implication, or use the technique that I use here to do that conversion. All right. Okay. Well, we do have one more class meeting before the assignment is due, which is next Monday. So that means, try to work on this as much as possible over the weekend. On next Monday, if you're really stuck and have no idea how to proceed, then we can talk about it in class. How does that sound? All right. Okay. So there is that. And now we're getting back to what we talked about last time, which is Lotto, right? But we're going to talk about this in a much more formal way, and this is the module actually linked from Canvas. So if I were to get back to Canvas and look at the modules, we are currently in discrete probability, and this is the module that I am displaying over here as module 0305. Okay, so I just want to show you guys where to find the module that I am using in today's lecture to explain, certain concepts in counting. All right, so first thing first, we're going to go over some terms. So the first term is what we call a trial. A trial is a single attempt to do something, typically involving choosing something. A single choice is a trial. All right, so I'm just going to pause here and kind of use examples to illustrate what a trial is in some real, actual activities. If you flip a coin, that is a trial. If you draw a ball, like Lotto, out of a basket with a lot of different balls with numbers on those, that is a trial. So it is one activity that has a result that is individual. You cannot break it apart into smaller parts. Does that make sense? Or does anyone have any questions about that statement? If you play a Dungeon and Dragon games and you throw the dice, throwing a single dice is a trial. Okay? So any questions about what a trial is? Okay. All right, so we kind of know what a trial is. So a trial has a set of possible outcomes associated with it. Each outcome represents a possible result of a trial. So we are looking at the result of an action. You flip a coin. Flipping the coin is a trial. What are the outcomes of that trial? Yep, head or tail, right? If you throw a six-faced dice, what are the possible outcomes?
1 through 6.
1 through 6, very good. And we do have dice that have what, 20 faces? Is it up to 20 faces for games?
For tabletop games, usually, yeah.
So you can have six, and what is the next one up?
8.
6, 8, and then 20?
6, 8, 12.
Oh, there's 12 too? Okay.
There's also 4.
And also, oh, right, 4 is a triangular faces, right? Okay. All right. If you have a ball of have a bag of numbers, from 1 to 69, and you reach into the basket and you pick a number out, what would be the set of outcomes in that case?
1 through 69.
1 through 69. Okay, so you have 69 elements in the set, and each one is an integer between 1 and 69. Okay, very good. So I think we're getting the idea of what a trial is and what an outcome is for a trial. So an experiment is just a series of trials where subsequent trials may be affected by earlier ones. Okay, so we'll just kind of focus on this part here. So an experiment is a series or a sequence of trials. So that means you can say, I'm going to flip this coin 5 times. So when you flip the coin each time, it is called a trial. But when you're done flipping the coin 5 times, it is called an experiment. And that's basically what it is. An experiment is nothing more than a of trials. Are we good so far? So now an experiment can also have its own outcomes, but let me explain this part here, where subsequent trials may be affected by earlier ones. If you're flipping a coin, it does not apply, okay? Because if you flip a coin, it would have two possibilities or two outcomes, which is head or tail. But if you flip the same coin again, well, guess what? You will still get head or tail. If you flip it again, it's going to be head or tail. So that means the earlier trials does not affect the outcomes of the later trials. On the other hand, if you have a bag of marbles, okay, and we'll just for labeling, we'll just label the marbles A, B, C, D, E, F. Okay, so there's 6 marbles. And the trial is just reaching into the bag and pick out one single marble without putting it back into the bag. So for the first trial, you have 6 possible outcomes because any one of the 6 marbles can be the one that you picked up. So for the first trial, you have A, B, C, D, E, F as possible outcomes. But for the second trial, it depends on what you took out in the first trial. So if you took out marble A in the first trial, then the second trial has only 5 possibilities or 5 outcomes, and those 5 outcomes would be B, C, D, E, F exactly. If you took out marble B in the first trial, then the second trial also has 5 outcomes, but those 5 outcomes would be A, C, D, E, F, because marble B was already taken out of the bag from the first trial. Does that make sense? So that is what I said, that's what I'm talking about, where subsequent trials may be affected by earlier ones, because what you took out is not put it back into the pool, so you cannot have the same outcome, multiple times. In general, the outcome set of an experiment is represented by the Greek symbol omega, which has nothing, absolutely nothing, related to the omega in the discussion of propositional calculus. There are only so many Greek letters and English alphabet, letters, so we sometimes have to recycle. Not to be confused with the set of operators in propositional calculus. There we go. So let me see if there are any questions related to what a trial, what an experiment is, and what is an outcome. So we don't have any questions about those? Okay. All right, so we're going to talk about general counting. Okay, so we are just counting. Um, just like what we did on Monday, we were counting the total number of possible tickets for the Powerball Lotto. So we're just doing counting in this case. So generally speaking, we are counting the outcomes of an experiment. So this is important. We are looking at basically the cardinality of omega. We are looking at the number of items in the set of outcomes for the experiment. That is usually something that is important. There may be other things that's also important, but the cardinality of omega is almost always important. So in the case of lottery, we may be counting the number of unique lottery tickets. If T of I is representing the outcome set of trial I, so we have trial 0, trial 1, trial 2, trial 3, and so on. In the case where Ti does not influence T of j, where j is greater than I, all this is saying is, no matter which trial we are talking about, it has the same outcome set. Okay, that's what this particular statement. Where's my cursor? Right here. So that's basically what this statement is trying to say. Is the outcome set remains exactly the same no matter which trial we are talking about. Then the outcome set of an experiment of m trials is going to be the Cartesian product between t0 and t1, and then take that and do another Cartesian product with t2, and then do another experiment, and then do another Cartesian product with t3, and so on, and all the way to t subscript m minus 1. Is that making any sense? If it's not, I have a pictorial way to look at this that will make more sense. Do you guys want to see the more pictorial way? Okay, so let's go ahead and do that. And to do that, I have to display this and then display the journal on my side, which is here. Unfortunately, the person who's online would not be able to see this because I have the recorder recording the browser. So that person will probably need to wait a little bit until I upload the video. And the time is currently it's 3:55. So the person who's online, can actually get to the right time mark to locate this segment of the video. But I can describe what I'm doing here. So let's talk about, three coin tossing. Okay, so we are basically flipping a coin exactly 3 times. So each coin flip is a trial. Every single trial has 2 possible outcomes, which is head or tail. Is that okay? So now we start from here. This is the beginning of the experiment. So for the first trial, we have 2 possible outcomes. We have head or tail. That's trial 0. And the set of the outcome of trial 0 is exactly in the set head, tail. There are 2 elements in that set. So now we try to conduct the second trial in the experiment. So here we have the 2 branches because you have head or tail again, head or tail again. Is that making any sense? So what about the third trial? The same thing. This is a binary tree because we have 2 outcomes for every single node. So after 3 trials, this is the exact tree that you end up with. Okay? So now the question is, what is exactly an outcome of the entire experiment? So my proposed way of expressing that is to say the set of head and tail, Cartesian product with the set of head and tail, Cartesian product with the set of head and tail. Because what that will give you, okay, so if you think about, head, tail, and I'm going to use the notation of power to represent, how many times we're doing the Cartesian product. So when you do that 3 times, then you end up with a set that has head, 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 tail, head, tail, head, head, tail, 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 head, 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 tail, head, tail, 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 head, and tail, tail, tail. Does that make sense? But are we seeing that at the leaf nodes? So each leaf node is not exactly just head or tail. It is also the accumulation of what happened before. So when you get to a leaf node, you kind of have to look at the entire path. So we have head, head, head to get here, head, head, tail to get here, head, tail, head to get here, head, tail, tail to get here, and so on. So you can see how the Cartesian product method and the tree method came to the same conclusion. All right, so I'm going to pause here and see if that is making any sense. Okay, that's all good? All right. So let me go back to the slide because a lot of times we don't really care so much about the actual outcome. We just want to do the counting. In other words, we want to figure out the cardinality of omega. So Cartesian product is used because for each element of T0 as the first actual outcome of the first trial, every f that is an element of T1 can be the outcome of the second trial and so on. So I'll illustrate the same thing, but this, next time I'll use a bag of several marbles, okay? Because that will also be useful to illustrate, what happens when um, an earlier trial affects the possible outcomes for the later trials. So for counting purposes, the outcome space has the cardinality of, this is a big pi notation, which means we are looking at a product of each individual term, and each individual term in this case is the cardinality of T of I, which is representing the outcome set of trial I, and I itself goes from 0 to m minus 1 because m is the number of experiments. Is that okay so far? All right. Okay, so I'm going to go back to the picture, and this time we'll take a look at a case where, well, what if, we are taking marbles out of a bag, which means, we are not, it's not going to be like this. So let me make a new page. All right, so this time we have a bag of 3 marbles, A, B, and C. Okay. So this time, when we look at the first trial is easy. It can be A, can be B, can be C, right? A, B, C. So that's the possible outcome after one single trial. Okay, that's easy peasy. But the second trial is not going to be as uniform as the one before, because in this case, the second trial, it has to look at the remaining choices. In other words, if A is chosen already, then the second trial only has 2 possible choices left, which is B or C. If B is already chosen in the first trial, then the second trial can only use A or C. If the first trial has C already, then the second trial only has A or B available. Is that making any sense? Okay. So now we look at the third trial. So the third trial doesn't really have a choice anymore because you have 1 marble left in the entire bag. So this is what it's going to look like. Okay, CBA, there we go. So when we want to look at each outcome of the experiment, then it becomes a set of A, B, C, A, C, B, B, A, C. Since there are only 6 items, I'm going to spell them all out. C, A, B, and then we have C, A, B, and then C, B, A. And you can also see how I am using parentheses in this case. So they are tuples, which means ordering is important. I'm looking at permutations and not combinations. Are we okay so far with this discussion? Okay. Oh, wait, hold on a second here. One more thing that's important about this picture. If you look at the cardinality of the omega of the entire experiment, does that match the product of the cardinality of each outcome set every step along the way. So let's think about that. The first trial has the omega of t being 3, because we got 3 choices when we try to pick out the first marble out of the bag. The second trial only has 2 choices, because we got 1 out of the bag already. We only got 2 marbles remaining in the bag. So that means the cardinality of the possible outcomes of each trial for the second trial is only going to be 2. The third one only has 1 choice, because out of 3 marbles, 2 are out already. So there's only 1 marble left in the bag. So it's not really a choice, because when you pick it out, you know exactly what it's going to be. So the cardinality is only 1 for the last trial. So when you look at the cardinality of the outcome set for the first trial, which is 3, we look at the cardinality of the outcome set for the second trial, which is 2, and then we look at the cardinality of the outcome set of the third trial, which is only 1. 3 times 2 times 1 is 6. Now, this is a poor example. I did not think about this, because 3 plus 2 plus 1 is also 6. But no, we are not adding, okay? We are multiplying. I want to emphasize, we are multiplying because of the phrase that I just used, for each, okay? So for each is a really important keyword, because every time I use for each, it's implying, not always, but it's implying strongly that we are dealing with multiplication and not addition. So is that okay? All right. So now we're going to go back and continue with the notes. So without replacement. So wait, there's one more thing. In some cases, the set of outcomes are the same for all trials, which is the case of the coin tossing case. So in that case, t of 0 and t of 1 all the way up to t of m minus 1, they are really the same thing. In the case of tossing a coin, they're all the set of head, tail. Okay, so they're all the same, which means they all have the same cardinality. So if they all have the same cardinality, then we only have to know what is the cardinality of one set, and then the actual outcome becomes n to the power of m, where n is the cardinality of the set of outcomes for each trial, and then m is the number of trials. Is that okay? So let me ask a question. Okay, let me count the number of people here, because this is a really interesting problem. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 12, 16, 18. So we got 19 people in class right now, okay? So I'm gonna write down 19 people. Okay, so I'm gonna open a new, oh, I can do it here. So we have 19 people. So I'm asking, if I were to look at just the birth date, so I don't care about the birth year, just the date of the birth, and we'll assume that we don't have any leap years, okay? So I'm asking about how many ways can as a class like this, including myself, out of the 19 people, how many possibilities are there about the assignment of birth dates?
365.
Each person has 365 days to choose from, but as an entire class of 19 people, what would be the total number of ways to arrange birth dates amongst the 19 people? You can just give me the equation, because it's going to be hard to do calculation, mental math. In this case, it's going to be very difficult.
Wouldn't it be 365 root n?
365
Oh, to the power of n.
to the power of, and we have 19 people,
Yeah.
right? To the power of 19.
Yeah, the reason why I said n was because the number of people.
Right.
Sorry.
Yeah, in the notation, I got it flipped, because n is representing the number of possibilities per trial,
Mhm.
and then m is representing the number of trials.
Okay.
So in this case, a single trial is one person, Okay, when I ask a person like when is your birth date, that is one trial, and there are 365 possibilities from each person. But just because you got a certain date for your birthday doesn't mean that you cannot have the same birth date, right? So that means we are not taking that date out of the pool, and that's why we are having a 265 to the power of 19 in this case, because every person, in theory, we can all have the same birth date. There's a very slim possibility, but it can happen. Is that okay? Does that make sense? Okay. All right. So kind of remember that example. Okay. So with 19 people, there are 365 to the power of 19 ways to arrange birth dates. Okay, this will become useful in just a little bit. I'm looking at the time, and I think we can go ahead and talk about that now. Okay. Okay. So this is an interesting problem, and well, it's not too interesting, but nonetheless, when you look at the actual outcome or the numbers, it might surprise you. Okay. So the question is, what are the chances that at least two people in a class share the same birth date? Not counting the year, just the birth date. Okay? So you might think, that's going to be pretty slim. It is slim earlier, and then as the class size increases, it becomes actually very common that at least two people in the class would share a birth date. Is that okay? So it's good to say, how it is interesting, but how do we come up with those numbers, right? So that's what we're trying to figure out. So now I want to look at what about the chances of at least two people sharing the same birth, birth, I cannot spell, date. Okay, so this is what I'm trying to figure out next. All right. Well, one way to look at this is to say everybody has a unique birth date, right? Because if I were to say it's the complement of that, okay? If you are interested in knowing the chances of at least two people sharing the same birth date, it would be the same thing as 1 minus the probability of every person has a unique birth date. Does that make sense? Okay, let's think about this from the perspective of quantifiers. As much as you guys are thinking, oh no, not the quantifiers again. Yes, let's do quantifiers again. So what this is asking is there exist at least two people in a set where the two people are not the same and they have the same birth date. So if you invert this, it becomes the same thing as asking, what are the chances that everybody has a different birth date than everybody else? Does that make sense? Okay, and that turns out to be a much easier way of looking at things, because if you say at least two people, that means there can be 3 people, 4 people, and so on. So that counting problem becomes just insanely difficult to deal with. But if you just want to say, well, everybody has a different birth date, that becomes easier. Okay, because now it becomes a problem of I have a gigantic bag, it has 365 numbers in it. Okay, each number is representing 1 day in a year. So I take the bag and say, take one number out, take one number out, and now there are 364 numbers left, right? I take it to you and you say, okay, take a number out. Now it has 363 numbers left, and I just do this to every single person in the class. Doesn't that kind of resemble the problem that we dealt with earlier with the lottos, right? So, okay, so now we look at that problem and we try to look at it from a tree perspective again, because I think the tree perspective really helps to make things a little bit more graphical. So now we have a tree where the first person says, I'm taking the first day of the year, and we're going to start with a 0 because it's 0 day away from the beginning of the entire year. And then the last person is going to pick out the last number, which is the um, day 364 of the day. Okay, so we are doing counting the way that programmers would do, which is starting counting the first one as 0, day 1, day 2 of the year. All right, but that means, okay, we'll take this one here. So if the first person takes out, day 1, then the second person can still take 0, but 1 is no longer available. 2 becomes available, and then all the way to day 364. Is that right? Okay, so that means at the very end here, if I want to look at the cardinality of this omega, what is it going to look like? And we have 19 people, right? This is the first person. This is the second person. We have 19 people. So what do you think omega, the cardinality of omega, is going to look like? Well, I just asked you a trick question because I did not tell you whether ordering is important or not. So now you guys will have to think about that a little bit and ask, is ordering important or not? Because in a lotto, ordering is not important. As long as the 5 numbers are chosen from the bag, like 1, 2, 3, 4, 5, it can be 5, 4, 3, 2, 1, 1, 2, 5, 4, 3. They're all considered the same, okay? Because I just care about, is this number a winning number? In the case of this, okay, in the class where I want to look at the birth dates of everybody, is quote unquote ordering important? How do we think about that problem? As it turns out, it is important. Okay, I'll give you an example. Okay, so let's just say that in the whole process of picking a birth date out of the bag, I picked out day 0. Okay, and you picked out day 1. So the question is that considered a different case compared to you picking out day 0 and I pick out day 1? It is different. Each one is a unique case when we count from the perspective of the 365 to the power of 19 number. These two are distinct. We should not combine those into one. So that is why ordering is important. Who gets which birth date is important. I'm not asking, is someone in the class getting this birth date? I'm asking who got that birth date. Is that okay? Does everybody understand the difference between those two statements and the significance of that? So ordering is important. So that means the cardinality is really just taking I going from 365 and multiplying, oh, not sigma, okay, it's pi, big pi, and it is I going from 365 down to 365 minus the number of people. In this case, it's 19 plus 1, so it's actually 365 minus 18. That would be the size of the omega. So this number, whatever it boils down to be, forgot what I'm multiplying. So what I'm actually multiplying is just I itself. In other words, this is just a fancy way to say 365 times 364 times 363 all the way down to 300 and, oh, my math is bad, 47, I think. Okay. So this product, which is going to be a pretty big number, is the number of cases where each person gets a unique birth date. Okay, this is the total number of ways of assigning birthdays in the class of 19, where everybody has a unique birth date. So when you divide this number by the other number, so we'll take this number and call this, okay, I'm going to introduce this term here. This is 365, choose 19, and it's the number of permutation. So if I take this number and I divide it by 365/19 and divided by 365 to the power of 19, which is not caring about whether people have duplicate birthdays or not. 365 to the power of 19 is no restrictions whatsoever. I want to know how many ways I can have people pick out birth dates in the class. So when you look at the ratio between these two, it becomes a probability. It becomes the probability that everybody in class has a unique birth date. But remember, our original problem is what are the chances that at least two people share the same birth date? So that means I'm looking at the complement of this number, which is 1 minus that. Are we still doing okay so far with that? Okay. So the question is, how do you think the number of people in class is going to impact the probability of how many of the chances of at least two people have exactly the same birth date in the class? So let's work that out because I think we got enough time to work it out using a spreadsheet. So we'll go ahead and use a spreadsheet, or any spreadsheet program can do this too. I'm just looking at, there's a spreadsheet here already. What is it? Oh, okay, great. This is a great spreadsheet to work on. So this becomes a Powerball and what we call the birthday problem. So now we look at the number of people in class. Okay, so number of people in class. We'll start with something stupid, like 1. What if there's only one person in class? What are the chances that this person is sharing a birthday with somebody else? Okay, don't answer the question because I want to generalize and use an equation to do it. And then we have this number plus 1. And so we can just like that, go all the way to say 45, okay, 44 people. And this one is going to count the number of ways of assigning birth dates, okay? So that would just be 265, to 365 to the power of the number of people in that class. Okay, hardly exciting. Okay, and again, you'll go all the way to 44, and I can do all this, as one, single step at the end of this. Okay, and for this, I'm gonna change the column size here, and then this one here is the number of ways of unique birth date assignments. So this time I have this restriction of, well, we don't want people to have duplicate birth dates, so we have to use that equation that I showed you earlier, which is the P of 365 choose a certain number of items out of. So in a spreadsheet, it is called permut, okay, which stands for permutation. You have to tell it what is the number of outcomes in the first trial, and then you have to tell how many trials we are talking about here. So the number of trials is the number of people in class, so I'm just referring to that cell over here. So, and okay, we can also always duplicate that later. So the next column is going to say what are the chances that all birthdays are unique. Okay, so this one is the chances of all birth dates are unique in the class. So that one is just a ratio, and I think I put this in the wrong spot. Copy, paste, delete, and make this column wider. There we go. Okay, so the chances is really just this number divided by that number. And it turns out to be 1 when there's only one person in class. And it is 0.997 when there are 2 people in class, and so on. Does that make sense to you, that if you have like 2 people, the chances of those people sharing the same birth date is pretty slim? Because the first person has 365 to choose from, the second person has 364 to choose from. So that's only off by 1 day, right? So the chances is pretty high that they do not have the same birth date. Okay, we are almost done here. I know we are running out of time. So now we look at the chances of at least 2 people sharing the same birth date. There we go, which is just 1 minus the number in column D. Okay, so 1 equals 2, 1 minus this number. Okay, so in the class of 1, well, guess what? You only got one person. So when I ask something about at least 2 people, not gonna happen, right? So now we're gonna look at the class of 2 people, 3 people, and so on. Pretty slim chances. Now, if I work it up to 44 people in the class, let's see what the chances are. Okay, so we'll keep going like this until we get here. Look at this. If we have a class of 44 people, the chances that 2 people in the class sharing the same birth date is 93.2 blah 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 percent. That is pretty high. We know this number, the number of column E, is going to increase as there are more and more people, but I think most people would not expect it to increase this quickly, right? Because if you think about it from a more intuitive but incorrect way, 44 divided by 365 is like, what?
Like 9.
About a ninth, right? This is not ninth. It's not even close. So this is the interesting problem that we call the birthday problem, which is asking what are the chances that at least 2 people in the class share the same birth date, and it turns out to be much higher than most people expected. But we came up with the answer using the technique that we just talked about today. So I want you guys to kind of think about it over the weekend in addition to trying to get the assignment done. And if you try your best, you cannot get the assignment done, on Monday, we'll talk about it. All right, so have a nice weekend. I'll see you guys all on Monday.